Today, we're going to be configuring a PIC microcontroller to interpret a button and a rotary encoder. This isn't the first time we've configured the PIC microcontroller to do stuff. Over the last 3 or 4 episodes or so, we have been diving into some various features of this PIC microcontroller and applying them in assembly language. So if you haven't seen the last few episodes, and this is the first one, you're kind of diving into this microcontroller assembly series, I highly recommend you go catch up because there are going to be some concepts that you're unfamiliar with. And if you are caught up, then you're probably aware that this is episode 36 or so of the grand scheme of us building and designing a digital illumination system. So, if you are all caught up, let's dive right in. Here's a schematic of the current circuit we have right now. There's the PIC microcontroller in the center. We have our power and ground over here on the left, and we have a couple of programming inputs here on the top, and the rest of this is all required circuitry that we talked about in previous episodes. We finished off the last episode with these 2 LEDs that are connected to RC4 and RC5, and serve as the outputs for timer 0 and timer 1. Right now, they're going to be going blinkety blink, and we're going to leave them alone for the time being. The remaining pins on port C are left open. On port A, most of the pins are used for programming. We do have an external clock input into RA4, which we're no longer using, and we're going to get rid of later on in this episode. And the remaining 2 pins are grounded through these resistors because all of the port A pins are currently configured as an input. We're going to change our circuit to look like this. Here's our button connected to RA2 through this debouncing circuit. In an earlier episode, we talked about how the signal from a button can be fairly messy and needs to be cleaned up. And so you can use this concept called hardware debouncing to clean that signal up through the use of a couple of resistors and a capacitor. And if you're interested in that, make sure you go watch the earlier episode. You can see the hardware debouncing circuit that we used here, 2 47 kilo ohm resistors and a single 22 nanofarad capacitor down here. We also have a new LED here grounded through this 1 kilo ohm resistor connected to RC3. We're going to use that LED to observe the button presses. Let's wire it up. With that all wired up, let's move on to the assembly code. We're going to start real simple and basically write some code that says whenever the button is pressed, the output LED will turn on. As we release the button, the output LED will turn off. And here's our code as we left it. Well, actually not quite as we left it. You'll notice I added a few comments to help me remember what's actually plugged into the microcontroller and which pin it's plugged into. So now that we've connected the button to pin 2, I'm going to change this line to reflect that. Then we'll move down to the main loop and add a few lines of code. First, we'll switch to bank 0, then observe pin 2 of port A. If the pin is clear, we're going to assume that the button is not pressed. And in that situation, we want to ensure that pin 3 of latch C is clear. However, if it is pressed, we're going to branch forward 2 lines where we use the BSF command to set pin 3 of latch C, and then restart the loop again. Now let's assemble this new code and program it onto the microcontroller. And looking at our breadboard, we can see our 2 timer LEDs are going blinkety blink, which we're going to ignore from now. And there's our output LED, but notice it's on and I haven't pressed the button. When I do press the button, the LED turns off. See, this makes a lot of sense. Because of the way that we've designed our debouncing circuit, the button input on pin 2 is idling high when it's not pressed. When we press the button, we're grounding that input. So in order to rectify the situation, all we need to do is invert the test. So rather than skipping the next line when pin 2 is clear, we will skip it when it's set. Now if we assemble and program this, it behaves as we expect. Okay, that was super easy and it works perfectly. But if you remember some of my gripes from the previous episodes, I think this method of coding is a little bit lazy in my opinion. What we're doing right now is we're putting it into the main loop. So that main loop is going through like over 100,000 times a second. And each time we are testing the condition of port A and then outputting that condition to the latch. And we're doing that like over 100,000 times a second. What I'd rather do is observe the port for changes in its value and only then send the output to the latch. Now, there's a way we can do that, and that is through another peripheral. Specifically, this one right here, this capture, compare, and PWM module. You remember in the previous episode, we talked about timer peripherals, and the idea behind a peripheral is that it allows you to delegate a task. You just configure it, and it goes off and does its thing. Well, this peripheral allows us to delegate the task of capturing a change on an input. Examining this closer, we can see that we can set a capture mode for every rising or every falling edge. So theoretically, we could configure this peripheral to capture the falling edge on pin A2, which would be the button press. And then once we've detected that the button has been pressed, we could reconfigure the peripheral to then detect the button release or the rising edge. And that would work perfectly fine, but there's a better way. Many microcontrollers, this one included, has multiple CCP modules. So we could configure one of those modules to detect a falling edge and the other to detect a rising edge. But if we look at the pin allocation tables, we'll see that the CCP2 input is on RC3 and the CCP1 input is on RC5. We need both inputs to be pointing to RA2. And, well, we know how to do that. In the previous episode, we went through this PPS, or Peripheral Port Select capability of this particular microcontroller. Lots of microcontrollers have it, so we could use that capability to reassign the input pins for CCP1 and CCP2 to RA2. And we do that by simply writing the appropriate value to the CCP1 PPS register and the CCP2 PPS register. The value that we need to assign can be determined right here. We want both of those peripherals to point to port A, pin 2, which would result in a register value of 000010, or hexadecimal 02. So let's create a couple of lines of code to move the value 02 into the register CCP1 PPS and CCP2 PPS. Don't forget to assign the bank. Both of these registers are in bank 61. Now that the peripherals are observing the correct input pin, let's configure them to detect the rising and falling edge. The mode select to capture the falling edge is 0100, which would be entered into the lower nibble of this register. The upper nibble contains an enable bit, an unused bit, the output bit, and an FMT bit, which we're not concerned with at all right now. So we want this register to read 11001000. And in hexadecimal, that is C4, which we will put into the CCP1 control register. The mode value for the rising edge is 0101, and so the CCP2 register should be configured to hexadecimal C5. Both of these registers are in bank 6. Now that we've configured both CCP peripherals, let's write the code to perform the tests to recognize when they've detected one of those edges. And just like our timer peripherals, we're going to use software interrupts. Bit 7 in register PIR1 will let us know that a capture has occurred for CCP1. The flag for CCP2 is available in PIR2, also on bit 7. So in our code, we can remove this business and add in a line where we test bit 7 of PIR1. If that flag is set, that means the button was pressed and I want to call an appropriate handler. We also want to test bit 7 of PIR2. And if that flag is set, that means the button was released and I want to call the appropriate handler. Let's write our handlers here just below our timer 1 handler. When we first detect the button press, the first thing that needs to happen is that the software interrupt flag must be cleared. Then in bank 0, we need to set bit 3 of latch C, indicating the button has been pressed. And then before ending the subroutine, we set the bank back to 14. The button release handler is awfully similar. We need to clear the flag, and then clear the third bit of latch C to indicate the button has been released. Then set the bank back to 14 and return out of the subroutine. With that done, we can assemble and program. Oh, look at that. Operates as expected. Now these amazing peripherals can be used for more than just capturing events. They can also be used to time certain events. Perhaps like how long I hold down the button. There's a little section in the datasheet which describes the compare mode of this peripheral. And basically all it will do is it will let us know when one full 16-bit cycle of timer 1 completes from the moment we start the compare mode. And it'll let us know by doing one of these things like toggling, setting, clearing, or generating a pulse output. So obviously this is dependent on the operation of timer 1, which is why we configured this in the previous episode. And it tells you this in the datasheet that timer 1 must be running. And it also highlights in this little important block that timer 1 must be clocked from the instruction clock or an external clock source. Now, if you remember, when we finished the previous episode, timer 1 was not configured to either of these settings. Rather, it was configured to the fixed 1 MHz source signal. However, in the datasheet, that source is not included in the valid clock sources. But because our system clock is running at 4 MHz, our instruction clock also happens to be running at 1 MHz. So I thought, let's give it a try. And basically, during the testing, it worked perfectly fine. So the way I interpreted this statement is that in order for this to work, the timer 1 clock can be no faster than the instruction clock. If you know for sure that this won't work, please let me know in the comments because my testing shows that it's working perfectly fine. So the specific action that I want to configure for the compare mode is to set the output, which means that in the compare set mode, the peripheral will wait for 1 full cycle of timer 1 and then set the output. And based on our timer 1 frequency of 1 MHz, we know the period is 1 microsecond. And since timer 1 is a 16-bit register, it will count to 65,536. Which will take just over 65 milliseconds. We need to know when that happens, so let's wire up another indicator LED to RC2, and we can create an event handler to simply turn on the LED on RC2 once the compare action in this peripheral is triggered. Now we need to be careful when handling that event. As we saw earlier, bit 7 of PIR1 will let us know when the capture has occurred. But it's that same bit 7 in PIR1 that also lets us know that the compare match has occurred. Which means that when the event handler is triggered, we need to be able to determine whether we are in capture mode or compare mode. So to help determine that, I'd like to use one of our general purpose resistors to remember the button state that we're in. And then we can test this register when we enter the handler to make the appropriate action. Let's also adjust this comment to demonstrate that this handler will handle both the press and hold functions. Now let's create those actions. Immediately after clearing the interrupt flag, we want to disable the peripheral. And then we want to make sure we initialize that register at 0. Which means it always starts in a released state. Then we're going to increment our button state. So if the button was released, it's now pressed. And if it was pressed, it's now held. Remember, this handler will be triggered in either capture or compare mode. So by incrementing the button state, we cover both scenarios. Then we simply test the button state to determine which mode the CCP module was in. And if it was in compare set mode, we want to set bit 2 of latch C to indicate that the button has been held. If it was in capture mode, we're going to branch forward 2 lines to set bit 3 of latch C to indicate the button has been pressed. And in that case, we then want to switch modes to compare set and re-enable CCP1. In the scenario where we determine the button was held, we'll simply branch forward 4 lines and leave the CCP1 peripheral disabled before returning out of the subroutine. Okay, so that's enough for the press and hold event handlers, but we still need to adjust the release handler a little bit. In our release handler, we're also going to initially disable the peripheral and then immediately re-enable it to capture every falling edge. And we also want to clear the button state and bit 2 of latch C. Because when we release the button, regardless whether it was held long enough to be registered as a long button press or a quick button press, all the LEDs or the indication LEDs will turn off. All right, and we'll assemble and program. Oh, look at that. You might be able to notice how our second LED lights up shortly after the first one. I think that's exactly what we expect because we know our button hold is for 65 milliseconds, which is an awful short amount of time. And we can actually confirm that on the scope. The yellow line up top is the button hold indicator, where the blue line is the button press indicator. And if I try to capture the delay between those pulses, we can see that it's just about 65 milliseconds. And if I try to make a really quick press of less than 65 milliseconds, I can sometimes get it so that the second LED doesn't light up. And you can see it on the scope. I'm only able to do it sometimes, because 65 milliseconds is really short. Let's extend it a little. So looking at our delay calculations, we can determine that there's really not a lot we can do to adjust this timer 1 delay, because the number of cycles that the timer 1 has to go through is always going to be a 16-bit register count. So the only flexibility we have right here is to change the timer 1 frequency. And in the timer 1 chapter of the datasheet, we can see that there are some options for that frequency. And if you recall, we had set it to the 1 MHz SF value over here. So I wonder if perhaps immediately after we detect the press, we temporarily slow down timer 1 to extend the hold time. And then once the compare mode triggers, now that it's being done slowly, we can then return timer 1 to its original faster speed. That might work. And based on our options, if we slow this down to the MF32 kilohertz clock, we get a period of 31.25 microseconds, which results in a timer 1 delay of about 2 seconds. Now that sounds like an appropriate delay. So the two configurations for our clock speed will be 00101 for the fast speed, which equates to hexadecimal 5, and 00111 for the slow speed, which is hexadecimal 07. So let's define a couple of constants in our code with those values. And then when we originally initialized timer 1 in our code, instead of using the fixed value, let's use our constant. And then when we detect the press, let's adjust the speed of timer 1 to the slow constant. Don't forget to adjust the branch since we added 3 lines of code. And then speed it back up to the fast value upon button release. Assemble and program. And let's test it. Oh, interesting. So as soon as I press it, you can see the timer 1 LED slow down significantly. And as long as I release it before the 2 seconds is up, the second indicator never turns on. But if I hold it for long enough, there we go. That's a 2-second delay, which serves nicely for an extended button press. We can even see it on the scope. If I don't hold the button down long enough, we never see the indicator on RC2 go up. But when I do hold it down long enough, it does go up. And the width of that entire scope window right now is exactly 2 seconds, so it works perfectly. And finally, we can get to the rotary encoder. Now, a number of episodes ago, we already went through all the details for the circuit that's required to get one of these rotary encoders to work. It's not all that complicated. I'll put a link in the description so you can review it if you need to, but we're basically just going to use that same circuit over here. And here it is right here added to our existing circuit. There's the rotary encoder with the 2 leads, A and B, coming out, which are debounced using the same 47 kilo ohm resistors up here and the 22 nanofarad capacitors here as we're using for our button. And you notice that the leads are wired up to RA4 and RA5 on our microcontroller. I decided to use those 2 pins because RA5 was unused and available, and RA4 was being used for an instruction clock output from one of our previous episodes, and we're no longer going to be using that, so we can just disable it. We're also going to need to add 2 more LEDs to our output to indicate whether we're rotating right or rotating left. And we'll put those LEDs on the 2 remaining available pins on port C. Now, the other thing to consider is the specific rotary encoder that we're using here has these real chonky pins, which don't fit very well into the breadboard. So your rotary encoder may have some smaller pins, which would fit just fine. So you can use that. But for this, I actually had to solder it to a separate board. Now the board that we're using here is just a leftover board that I had from a previous design, which had space for that rotary encoder. And in the back of the board, you'll see that I put in the 4 resistors and the 2 capacitors right onto the board, so we don't actually have to put them onto the breadboard. You'll also notice a bunch of wires hanging off here because we needed to find, the leads to plug into the breadboard. So the black one is the ground, the red one is the power, and the 2 green ones are the A and B leads. So let's wire this up as well. I have some pretty nasty glare on that PCB because of my lighting, so I'm just going to cover it up with this. Okay, now that we're all wired up, let's talk about how we're actually going to detect the rising and falling edges of the rotary encoder. As we just did with the button, we know that we can utilize the capture mode of the CCP modules, but there's only 2 and we've already used them. But there is another peripheral we can use if we scroll down a little bit. It's called Interrupt on Change, or IOC. The IOC capability can be enabled on nearly every pin, and it's a whole lot simpler than the CCP peripheral because it just does that one thing. It detects a change. The operation is straightforward. There's a register where we can enable a positive edge detect, another register to enable a negative edge detect, and finally a flag register to tell you when that edge has been detected. And there's one available for each port, A, B, or C. So since we're using a rotary encoder, all we need to do is capture a negative edge on one of the leads. And once we capture that negative edge on one of those leads, we test the other lead to determine which direction the rotary encoder is spinning. And since our leads are connected to pins 4 and 5 on port C, we simply have to enable one pin for a negative edge detection. Let's choose pin 5. So in our code, let's adjust our comments to reflect that we're using RA5 and RA4 for rotary encoder leads A and B. We'll also adjust RC1 and RC0 to indicate the direction of spin. We mentioned earlier that RA4 was being used for an external clock out. We need to disable that functionality to make sure that we can now use it as an input. And that will be done right here in the config words. We're going to disable the clock out by setting clock out n equals 1. And we can confirm that right here in the datasheet. There's clock out enable, and if we set it to 1, it is disabled. Now we can add the line of code that enables the negative edge detection on RA5 by simply setting bit 5 in the IOCAN register. I added it into this block of code because we know that that register is in bank 62. Okay, so we've configured the negative edge detection on RA5. Now let's create the handlers to deal with when those edges occur. And just like all the other event flags we've been working with, the register PIR0 has an interrupt on change flag located in bit 4. But notice this one's a bit different. First of all, it's a read-only bit. In all of the other event handlers that we've created, the very first thing that occurs when we enter that handler is we go and we clear that flag. But we can't do that here because this flag is read only. And that's because this particular flag is a combination of a whole bunch of other flags. See, in our situation, we've enabled the negative edge detection on a single pin, but you can enable negative and positive edge detection for multiple pins. So you need to have a way to determine which pin was the one that triggered the event. And that's why we have this interrupt on change flag register, which tells you exactly which pin triggered the event. And this flag over here in PIR0 is simply the OR of all of the other flags. Lucky for us, since we're monitoring only one pin, we don't have to dive into the individual interrupt flag registers. We can just use that one flag registers, which tells us that one of the IOCs was triggered. And then we can clear all of the flags that are in the individual flag registers. Kind of like this. Let's add in a line that will test the master flag. In this case, it's bit 4 of PIR0. And if that flag is set, we're going to call this handler. And we can create the handler up here. And when that handler is called, rather than clearing the flag in the PIR0 register, since we can't do it anyways, it's a read-only flag, we simply need to clear all of the action flags in the IOCAF register. Because we don't care about the rest of them. Clearing all of them is the same as clearing the one we're interested in. Now we have to determine which direction the rotary encoder is spinning. And I'm going to start by preparing a mask. Since the initial edge detection happens on pin 5, I'm now going to examine the status of pin 4. Because of the way rotary encoders work, if pin 4 is high, we're going in one direction. If it's low, we're going in the other. So if that bit is set, we're going to left shift the mask we just created. But if bit 4 was clear, then it's going to skip that left shift instruction. So now in the working register, either bit 0 or bit 1 is going to be set, depending on which way we move the rotary encoder. And then we apply that mask to latch C using our XOR WF instruction, which, as you know from the previous episode, will simply invert the appropriate bit. So if we're turning the rotary encoder in one direction, bit 0 will be inverted or toggled. If we're turning it in the other direction, bit 1 will be inverted or toggled. And since bit 0 and bit 1 are connected to our LED outputs, we'll be able to visualize the direction based on which LED is lit and the speed of our turning based on how fast it's toggling. Let's assemble and program, and let's test it out. Twisting it right turns on one LED, and twisting it in the other direction toggles the other LED. And our button still works. Not only that, the button and rotary encoder are both working simultaneously. Fantastic. It works beautifully. Now, there's one final thing that I'd like to do before we finish off today's episode, and that is activate the hardware interrupts. Now, there's a whole chapter on interrupts, and if you've done any research on interrupts at all, you'll know that they're a very powerful functionality of microcontrollers, but they can also make things really hard to debug. Now, we've been doing some preparation to get to this point of enabling our hardware interrupts by utilizing software interrupts. As you recall, we have those flags that turn on anytime one of these events are captured, and we're going in to disable or clear those flags each and every time. And in our code, we have a series of test instructions that are repeatedly looking for those flags. And by enabling hardware interrupts, all that really means is we no longer have to keep checking those flags. When an interrupt occurs, the hardware on the microcontroller will automatically raise the flag and send the code to a very particular spot. And that particular spot is right here, address 0004, or the interrupt vector. Now, we've talked about this in a previous episode, and I've always said, don't worry about it, we'll get to it in another episode. Well, now's that episode. But we've been preparing all along with these handlers that we've created. So really, there's not a lot of work we need to do to enable hardware interrupts. All we really need to do is populate some code at address 004 that will handle those interrupts. And well, we already have the code to handle those interrupts. It's all down here in our main loop. We can pretty much just take all that code and move it here. So now when a hardware interrupt occurs, it will immediately go to address 004 and it'll start proceeding through the code that we've already defined to determine which interrupt was the one that triggered. And based on our existing code, it will already call the appropriate handler. And once the handler is done handling, there's one more instruction that we have to issue that will relinquish control back to the main program. And that instruction is retfie, which basically signals the end of the interrupt. Don't forget to remove this org directive. Now, all we need to do is turn the interrupts on. As we know, all the interrupt registers are in bank 14. We're going to start by clearing any residual flags that may have triggered during startup. Then we have to individually enable the interrupts. The first one will be the interrupt on change. And hexadecimal 10 equates to bit 4 of the PIE0 register, which turns on the IOC interrupts. Then I'm going to set the register PIE1 to hexadecimal A0, which will turn on the interrupts for CCP1 and timer 1. And for the register PIE2, set it to 80, which will turn on the interrupt for CCP2. Then we set another bit to enable the peripheral interrupts on the intcon register, which is kind of like a master peripheral switch. And finally, the global interrupt bit, which is bit 7 of the intcon register, right here, which is the big global master switch. You may also notice that the main loop is pretty much empty. And look at that, it's still working spectacularly. Ah, that was fantastic. We've got inputs, we've got outputs, we've got hardware interrupts enabled. We have all of our activities delegated to the peripherals. It is truly a thing of beauty. But you may have noticed that we're using a whole lot of pins right now for not a lot of output. I think we have 6 LEDs or indicator LEDs that are basically giving us information. And if we wanted to add more, we kind of can't, because we've exhausted all of our pins. So on the next episode, we're going to make use of another peripheral called the serial port, which will allow us to expand the indicator output tremendously. See you then.